Hello all. So welcome to this new lecture on peak detection and smoothing as a part of the course Signal Processing Algorithms and Architectures. This is Dr. Anirban Dasgupta and let's begin. So in time domain signal processing, we have several problems and we have covered things like time shifting and scaling, amplitude shifting and scaling, modulation, correlation, convolution and zero crossing detection. So today we are going to focus on peak detection and we will also cover topics like envelope detection, smoothing and pattern matching in subsequent lectures. So what is peak detection? So this is a technique in signal processing to identify local maxima and minima in a signal, and these are common things like what is a peak and what is a trough. So peak is basically a point in the signal which is higher than its immediate neighbors, and a trough is a point in the signal that is lower than its immediate neighbors. So why this is important? So these peaks and troughs can represent some significant events in the signal. I'll give you some real life examples. So what is the problem of peak detection? So this problem is to identify the peaks and troughs and the specific locations in time. So as per the definition, a point x of n will be considered as a peak if it is greater than its previous sample xn minus 1 and xn plus 1, that is the following sample. Similarly, a point will be considered as a trough if it is less than xn minus 1, that is the previous sample, or the following sample x of n plus 1. So this is a pictorial representation of peaks and troughs in a signal. The peaks are represented by red dots and the troughs are represented by green dots. So what are the applications? So if you see, in audio signal processing, this has a good application in beat detection. So whenever there is a beat, there will be peaks in the audio signal, and this is useful in tempo analysis, rhythm recognition and synchronization with visual effects in media. Also it is useful for detecting pitch in audio signals or typically sound waves, and this is useful in music composition software, auto tuning and sound analysis. In biomedical signal, peak detection has a hell lot of applications. So in ECG signals, for example, there is something called R peaks which is happening in QRS complex, and this is the highest point in the QRS complex, and this peak detection or the detection of the R peaks helps one to analyze the heartbeats and important parameters like heart rate variability. So you can diagnose diseases like arrhythmia, or it is also used in wearable devices like we have our smart watches, and this heart rate calculation is using some sort of peak detection algorithm. EEG signal, for example, is another area where peak detection is useful, specifically to find brainwave patterns like alpha waves, beta waves and theta waves. And this is helpful in analysis of sleep studies, like how is the quality of your sleep, whether you have epilepsy or not, or cognitive state monitoring such as how cognitively active you are, whether you are facing some kind of fatigue or tiredness. So these are using peak detection at the back end. In vibration monitoring and fault detection, this is useful like analyzing mechanical vibrations or predicting faults in machines. So this is also a very big application because a lot of faults are happening in machines in the industries, and a lot of money is wasted in this process in maintaining those machines. So if the fault can be detected in advance using some vibration signal or maybe some other signal using some sensors, so these devices or these machines can be protected or given proper care before any fault occurs. In seismology and earthquake detection, peak detection is a vital parameter specifically to detect earthquake, to locate and quantify the earthquakes, also in volcanic activity monitoring, to monitoring the volcano activities such as an eruption or a magma movement. So, these are just the tip of the iceberg, and there are a lot of applications of peak detection. So, let us now try to understand what are the peak detection methods. So, first method is thresholding, which is kind of a naive method. Then thresholding followed by smoothing, adaptive thresholding, using the first derivative, using the second derivative, and the windowing method like sliding window to find local maxima or minima. Now, in this terminology, often peaks and troughs are collectively called peaks. So, let us try to understand the algorithms. So, starting with thresholding. So, in this method, threshold are set, and any value of a signal, if it exceeds a threshold, say I have some signal peaks like this. So, to me probably this is not a good peak. So, if I set a threshold like this, so anything above the threshold, if I have this condition met, that x of n is greater than x of threshold, and also the immediate neighbor check like this point is greater than its neighboring points, then I will say this point is a peak. So, there can be lot of spurious peaks in the lower end of the signal. So, these peaks will not be detected if we are using a simple thresholding method. So, there are n comparisons, because you first compare with the threshold and you compare with the previous and the upcoming sample. So, the complexity will be O of n. So, here you see lot of peaks are detected using this thresholding method, and the threshold actually decides how many peaks will be detected. Like to me, this looks like a wave where there are two prominent peaks. This is one region of peak, this is one region of peak. But because of say noise, there are a lot of spurious peaks. So, we can change the threshold, and by increasing the threshold, we see that, so here with a low threshold many peaks are detected. As I increase the threshold, lot of spurious peaks are removed, and further I increase, I get less number of peaks, and with a threshold of 1 I get very few peaks. Maybe a threshold of 1.5 will give me exactly 2 peaks which I am looking at. So, what are the limitations of this method? So, although this method is very easy to understand, this method is highly sensitive to noise. So, if there are small fluctuations, those will be identified as peaks, which may not even signify any physical phenomena in the original signal. Then the fixed threshold problem, just like in the zero crossing detection, the fixed window size. So, here fixed threshold problem may be difficult to detect peaks, especially for non-stationary signals. So, here probably some adaptive thresholding will be beneficial. Then missed peaks, like if the threshold is too high, some peaks may be missed, or if the threshold is too low, you can have too many peaks. So, this is very much dependent on the threshold, and this is good enough to understand, but for applying in practical scenarios, you may need to do something else. And one of them is smoothing, because peak is a high frequency component. Of course, I have not introduced the concept of frequency so far, we are in the time domain. So, I will try my best to restrict myself in the time domain, but consider that there are peaks like this. So, maybe this is only one big peak, but there are small oscillations across the peak which will satisfy the threshold condition as well as the neighborhood condition. So, if I smooth this signal like this, you end up with only one peak, which is the desired peak. So again, as I said, smoothing techniques we will discuss later, but from the English word you understand that smoothing is something which is removing this abrupt fluctuation. So the general idea is to apply a smoothing filter like a moving average filter or a Gaussian filter or any low pass filter you can apply, and then use the threshold based detection method. So this is the algorithm. So you first smooth the signal using one of the filters as discussed, and then you apply the threshold. Now analysis of the complexity. So thresholding, we have discussed that only O of n complexity is required, but when we are smoothing, typically we are convolving with a filter of say size W, and this is, I am considering that we are using a linear filter, that is we are smoothing the signal by the convolution operation. So in such a case, the convolution will take a complexity of O of n dot W, where W is the filter size. And again, this is the naive way of convolving or the brute force method of convolving. If I use fast Fourier methods, then the complexity can become, instead of W, it will become log of W, log base 2 W. Now what we are doing is, so this is thresholding with smoothing. Now you can see that after thresholding and smoothing, so we see very less number of peaks or false peaks, I would say, as compared to the signal without smoothing. And in one case, like in this case, because of the thresholding operation, we are even reduced to only 2 peaks, but these two are not the actual or desired peak. Maybe here we desire only 1 peak, but we are getting 2 peaks. Of course, this can be mitigated by even further smoothing, but that is not the point, but this peak is missed. So selecting the threshold is again here creating the problem, and this is where the question comes, that blurring peaks. So your actual peak may be very subtle, and because of the smoothing process your peak may be blurred, and also because of the choice of threshold your peak may be missed. So this threshold problem can be adjusted by using some adaptive threshold, which will dynamically adjust itself based on the signal characteristics, such as the signal mean or standard deviation, and this will allow you to detect peaks with better precision, because the threshold will be now variable based on the local neighborhood of the signal. So the algorithm of adaptive thresholding is, first we will smooth the signal, and then we will use adaptive thresholding based on the properties of the signal, and I would say local properties, which means based on some small window. And if you compare these 3 methods, like just using a fixed threshold, using threshold, smoothing and threshold, and using adaptive threshold, of course with smoothing, so you will find that at each stage there is an improvement. So these are the things. Now again in this case, so we have taken several parameters of thresholding. Now here to me this is the best, where I am actually locating all the true peaks. Of course there are 2 false peaks, here we get 2 peaks, here we get 2 peaks, where there should be 1. But for the other cases, like these 2 cases, the peaks are entirely missed, and in this case we get only 1 peak. So this we can do some post processing, like comparing the distance between 2 peaks, and then we can boil down to the actual required peaks. So the advantages are that it is robust to noise because of the smoothing factor, as well as because of this changing amplitude and this dynamic thresholding, and using the local statistics we are able to detect better peaks or peaks in a better manner. But the limitations or challenges is the window size selection, that the local statistics which I was talking about. So, what window size it should be, how much to take, that is one question here, and that is typically dependent on your exact signal or the application. Then tuning the parameters like whether standard deviation is a good parameter or shall we use some other parameter for selecting the threshold is a big question. And of course, this does not address the issues of edges, specifically if you are using windows. So, at windows there will be lot of edges. So, for each window there will be 2 boundary values or edge values. So, how to handle them is again a question. So, one way is mirroring the signal, like use small portion of the boundary region and mirror them and see whether you get a peak or not. Now, let us come to the derivative method, and this method is analogous to the analog method in calculus, where we use our f of x derivatives to find the maxima and minima. So, the concept is that, so when we have a peak or a trough, so what happens is that, so my derivative, so if this is a peak, so there is an increasing part and there is a decreasing part. So, what happens is, so if you see the slope, so slope before this and slope after this, they are of opposite polarities. So, that is if the slope at the previous point and at that specific point, or you can also take one point ahead, that n plus 1, they will be of different polarities, and you can use the product to find whether they are of different signs, and then you can mark them as a peak, or not them, but mark that specific point as a peak. And the second derivative method is just like the local maxima method, not local maxima, but the maxima method used in calculus, where you do the second derivative test and check whether the second derivative is negative, which indicates that it is a maxima. Why it will be negative? Because my signal is increasing, and so the first derivative will be positive, and then after the peak my signal will be decreasing, which means the first derivative will be negative. So, which means that my rate is changing from being positive to negative. So, hence my double derivative will be negative. And similarly, you can detect a trough also, because since this is the same algorithm, just with the polarities and signs reversed. So, I am not explaining it explicitly. Or you can consider, since the peaks and troughs in signal processing concepts are synonymously used as peaks. So, you can take the absolute value of the signal and then apply all these techniques. And at last, we are interested to detect local maxima. So, this is again, you can take a small window, and in that window you can slide it and use the same technique. So, this technique is basically dividing the whole signal into sub signals and applying the methods on each sub signal, and then finally merge the peaks. Now, these windows may be overlapping and may not be overlapping. So, overlapping windows may solve some boundary problem issues, but complexity wise it may not be very good. So, if you are doing a real time application, it is not a very good way to take lot of windows and also take highly overlapped windows. So, if you are taking non overlapping windows and if you have the provision for parallel processing, then that is still very good. But with overlapped windows also you can do parallel processing, but still you will get a lot of windows, specifically if you are going for a very high overlap like 90% overlap or 75% overlap. So, thank you so much. So, these are the concepts of peak detection. We will get back to you for other interesting topics. Thank you so much.